Hi, everyone. Welcome to the second part and final part of Lecture 4 of Astronomy Geoscience 160. This is going to be a little bit longer than most of the other lecture segments, but it's a big topic, and we're actually going to split it up into two starting this week, and then we'll finish this next week. Basically, this lecture and the next lecture will tell the story of how we go from the very beginning of our universe to Earth as a planet. So today we're going to start off with the Big Bang. So last time we discussed the Big Bang in the first part of this lecture uh, in terms of how our universe must have come to be. We have observations showing that the stars, the galaxies in the sky, all seem to be moving away from our own galaxy. And the way that that makes sense is if everything is moving away from everything else, as if it started out all very close together and then over time started expanding. We call this the Big Bang Theory because presumably everything must have started with a Big Bang, a giant explosion. We have mathematical theory that lets us describe the evolution of our universe in this scenario. Now, our mathematical theory can only take us so far. We don't actually know the pure details of what happened. But based on what we know about our universe and based on what we know about physics, we can make some pretty good guesses. The further back in time we go, the harder it is and the more speculative things become. But from the time of, the first, the first second or so onwards, we're pretty good. So we think our physics can tell us pretty much the entire history of the universe, except for the very, very first few instants. And I'll explain later on where those parts are and why it's hard for us to do that. So, first of all, a couple of things we'll need for this lecture. And one of them is a review of scientific notation. So, you may have learned about this in some of your previous classes, but scientific notation is just a convenient way to describe very large or very small numbers. So, the way it works is you write a number as 10 to some power, and that power represents the number of zeros after the 1. So in this case, 10 to the power of 0 is 1 because there are 0 zeros after the 1. 10 to the power of 3 is 1000 because you have a 1 and then 3 zeros. And that is this many dots. So this is what 1000 looks like. Scientific notation helps you go very big very quickly. So I'm going to take 10 to the 3 and I'm going to add 3 more orders of magnitude to that, 3 more powers of 10. And that'll give me 10 to the 6 or a million. And we all know that a million is a lot, but just to give you an understanding of how much is a lot, I'm going to let you watch this video of me scrolling through a video or an image of a million dots. So I'm going to start here, and I'm scrolling pretty fast in this video, and there are a lot of dots. So that first line you saw pop up over here was for 100,000. So that's 200,000 now. So we're only 20% of the way through scrolling through this large image with a million dots. 400,000, 500,000. Somewhere in this, there is a red dot to indicate what it really means to be 1 in a million. I have not yet been able to find that 1 in a million dot, and I looked for a little while. If you were able to see it on this recording, that would be very impressive to me, so please let me know. But in the meantime, we're up to 900,000, and finally we're going to hit a million dots on here. And as the video says, sorry, a million dots is a lot of dots. And it's only 3 more orders of magnitude than the relatively manageable 1,000 dots that we had here. So you can imagine how much more absurd 10 to the 9 dots would be, a billion dots. It would be 1,000 of those images that we just scrolled through. So scientific notation lets you talk about extremely large numbers pretty easily and lets you think about numbers that are really inconceivable to humans, but we can think about them and do math with them and write them down conveniently like this. The other thing about scientific notation that I want to go over is what happens when you go to negative powers. So when you have 10 to the negative number, instead of talking about something greater than 1, we're talking about something less than 1. So it's the same way we would do it for 10 to the 3, except when it's a negative number, it's 1 in 1,000 for 10 to the 3. So the negative means it's a 1 in, and then the 3 is the number of zeros after the 1 in that large denominator number. So 10 to the 3 is minus 3 is 1 in 1,000, is 0.001. Here's an illustration of 1 in 1,000. So this black dot, this red dot over here is 1 in 1,000. 10 to the minus 6 is 1 in a million, or 0.000001. And I don't want to scroll through all of this again, but you could imagine that the one red dot, which is supposedly in this image, which I haven't found yet, is 1 in a million. And of course, we can scroll all the way through it and look for it, but that seems like a lot of work. So that's a review of scientific notation. And it'll be really important going forward because the Big Bang talks about some very, very small and some very, very big numbers. So we'll be really using it during this lecture. The other thing that's really important to understand about the Big Bang is that when stuff is compressed, and in particular when gas is compressed, it gets hot. Here's a demonstration of this process. So this fellow here has a plunger, and inside of this plunger is a flammable material. I think it's like a cotton thread or something. And what he's doing is he's compressing that plunger very quickly. That plunger is airtight. So what it's doing is it's taking the air inside of that plunger and it's compressing it significantly. The air heats up, the gas heats up when he compresses it enough that it ignites that flammable cotton material. And you can see the flash in there. So this is an illustration of what happens to gas when it gets compressed. And you can start to imagine why I might care about this, because when we're talking about the Big Bang, we're talking about gas and materials at very, very high densities, very compressed. So things are going to be hot. And it turns out that we've already discussed what happens in hot liquids. When we have things in a cold liquid, everything is moving around a little bit slowly. But when things are hot, they move around faster. And that's why the food coloring in this jar of hot water disperses much faster than the food coloring does in the cold water. Hot materials have particles that move around very quickly, and cold materials have particles that move around more slowly. This is important, again, for what happens during the Big Bang. It turns out that the key to the history of the universe is how the temperature changes over time. In the Big Bang, things start off infinitely close together and infinitely hot, or so we tell it. But when that is the case, temperatures must be nearly infinitely high. And this is what that would look like. So if we go back to a very small fraction of a second, right before the Big Bang on this graph, so on the x-axis here, we're showing time elapsed since the Big Bang. And on the y-axis, we're showing the temperature of essentially everything in the universe. The very small time since the Big Bang leads to a very, very hot temperature, 10 to the 32 or so Kelvin. So that's 10 with 32 zeros, 1 with 32 zeros after it. That's a lot of zeros. That's really hot. It's inconceivably hot for us. And this is also an inconceivably short amount of time. There are 10 to the 43 intervals of this amount of time in every second. So these numbers are just mind-boggling. But fortunately, with scientific notation, we can still talk about them and do math with them and think about them without really understanding viscerally what it means to be that fast or what it means to be that hot. And as time goes on, the temperature of the universe decreases because the universe expands. The Big Bang bangs and everything goes outwards. So the history of that evolution, the history of the temperature decreasing over time, is what gives rise to basically all of the structures in our universe. And I'll start talking about that right now. So in the first 10 to the negative 43 seconds after the Big Bang, we are essentially clueless as to what happened in our universe. And the reason is our mathematics and our physics can only take us so far. In physics, we know that we're missing parts of our understanding. We don't have a theory that describes everything perfectly. What we have is a bunch of theories that we think describe certain aspects of the universe very well and certain regimes very well. But when you get so hot and so dense and so massive, like the beginning of the universe, our theories just totally break down, and we don't think that they give useful information. So in those first 10 to the minus 43 seconds, we just have no idea what happened. As time goes on, we become a little bit more confident in our theories and we can start making some predictions. Although, of course, it's impossible to be 100% sure what happened without actually being there and without ever being able to take observations of that time. So, after about 10 to the minus 43 seconds into the lifetime of our universe, we think that our laws of physics start being able to describe how our universe worked pretty well. Now, we can't be 100% sure. We'll never be able to observe any light from this time in the universe, and I'll explain why later. So we can't entirely understand what's going on here, but we think we have a pretty good idea. So during this time, a few things are happening. Number one, the laws of physics are changing. When particles and everything is so hot and so energetic, things behave differently than they do at temperatures like we're used to here on Earth. And our laws of physics essentially have to be modified to be so hot. And things are cooling down and trying to essentially come to the way we understand them today. It's so hot that nothing can be held together. Remember how I talked about when we had ionized particles, particles that smashed into each other because they were so hot and they were enough to knock an electron away from a proton. That is happening here in overdrive. Even small particles like protons and neutrons can't stay together. And instead of those particles, we have even smaller subatomic particles called quarks that make them up. So there's this soup of quarks and electrons and things that essentially just can't break apart at all. And basically, everything is mixing together and crashing into itself. Energy and matter are basically interchangeable through E equals mc squared, and everything is totally chaotic. But over the next microsecond, things start to cool down. Another important thing about this early time in the universe, and for actually the first few 100,000 years of the universe, is that there's frequent collisions between light and matter. So, light, when it's traveling, there's so many particles, there's so many quarks, there's so many electrons nearby that the light waves crash into those and bounce off, and they just keep bouncing between different particles. So the light can't travel very far. And that means we can't really see anything from back there because all of these particles acted like a shield. The universe was essentially opaque. So after the first microsecond or so, things cool down enough for the first protons and neutrons to start to form. As I mentioned just a second ago, protons and neutrons are not actually the smallest particles that can make up other particles. Protons and neutrons are made up of particles called quarks. And in the second microsecond, up to the first second, these quarks start combining together into protons and neutrons. And there are different flavors of quarks and different types of quarks, and different arrangements of quarks make protons and neutrons. And this is when that starts to happen. Over the first few seconds to few minutes, things are cooling down even more. And because things are cooling down, everything larger is starting to come together. Now, in the first few seconds to minutes after the Big Bang, the first nuclei are forming. So we've used to have protons flying around by themselves and neutrons flying around by themselves. But now we're starting to get protons and neutrons sticking together. So the first nuclei that were made were called deuterium, which is a proton and a neutron. It's essentially a heavy flavor of hydrogen, where you have the same number of protons as a normal hydrogen, but you have this extra neutron, which gives it more mass. When you get enough of these deuterium atoms floating around, they can start to crash into each other and they can start melding together as well. And you can get things like helium, where you have two protons and a neutron stuck together. over the course of those first few minutes, we start forming a decent number of atoms and a decent number of nuclei in this way. This graph shows how much of different types of nuclei there are over time. So on the x-axis is time, going from about 1 second to the first couple of hours after the Big Bang. And on the y-axis, it's showing how much of the universe is made up of that thing. So the entire time you can see that there's a lot of hydrogen. There's a little bit more helium after the first minute or so. That starts to rise starting at about 10 seconds. And you can get these other elements here. So even beryllium and lithium start to show up after the first 10 minutes or so. But after that, things slow down quite a bit. So in the Big Bang, we actually end up forming some of the elements in our periodic table. And in particular, the ones that are formed are hydrogen, helium, and a little bit of the lithium that we have today, and maybe just a tiny trace amount of the beryllium that we have. Now, this may not look like many elements, but it's actually the vast majority of the mass of our universe. So all of the hydrogen you see, basically, the hydrogen that we drink in our water, was formed in the Big Bang. And much of the lithium that you see, it came from the Big Bang as well. Lithium is important to us in our technology because that's the basis of batteries for your computers and for your smartphones. So your smartphone perhaps came directly from the Big Bang. So by the end of the first 15 minutes to hour or so of the universe, this process kind of stops. You don't get larger nuclei forming after the first 15 minutes or so. And the reason for this is that things are now too cool for these nuclei to crash into each other anymore and stick together. They're not moving fast enough anymore. The temperature is low enough that they don't get close enough to stick together anymore. So really, there was only a very short window to create these elements in the Big Bang. The rest of the elements will have to wait until next lecture to be formed. So the next really important thing that happens at about 370,000 years after the Big Bang. And this is the formation of the first atoms with nuclei and electrons. So instead of just having nuclei stuck together, we now have electrons that are bound to these nuclei. Before this time, everything was ionized. All of the electrons were essentially separate from the protons and neutrons, but now they've come together. And what's really important about this process is now the electrons are not crashing into light so often, and the universe becomes much more transparent. So light can now pass right through these atoms unless it happens to be at exactly the particular color of light that causes a change in the energy level of the atom. But most light doesn't actually match the energy levels of hydrogen, so the light just streams on through. So the light from the Big Bang has therefore been traveling basically freely since 300,000 years after the bang happened. So we can actually see the glow from the Big Bang with our telescopes. The universe has expanded so much and everything has cooled off so much that the radiation, the light, the afterglow from the Big Bang is not light that we can see with our eyes. It's not visible light. It's actually radio frequency light. And it's fit almost perfectly by this black body curve here. This is data from a spacecraft called COBE, the Cosmic Background Explorer, which won a physics Nobel Prize in the 1990s. And the Explorer launched in the 1980s and 1990s, and then the Physics Nobel Prize was awarded in the 2000s, actually. Here's what the map of that cosmic microwave background looks like. It's pretty boring, right? There's not much to see here. It's very, very uniform. And that tells us it has to have come from the Big Bang, because when we look into our universe, nothing else is this smooth, nothing else is this uniform. But we can try to change our color scale and we can see if there's any slight deviations from this very uniform shade of green here. So now instead of having our color scale go from 0 to 4, let's zoom in to about 2.722 to 2.728 degrees Kelvin. That's the temperature of the radiation right now. very cold, but still visible. When we zoom in like this, we start to see this kind of pattern here. This is actually due to the Doppler shift of the radiation. The light from the Big Bang is shifted because we are moving with respect to the Big Bang's frame of reference. We are moving with respect to the universe. And this is the Doppler shift, that change in frequency, the change in color of light as we move in one direction and away from the other direction. So we can subtract this off and we can look for other smaller things as well. So this is what we see when we do that. You can see that there's a big red band across the middle here. This is actually interference from dust in our own galaxy. So you can just ignore that. But these blue areas here, these cold spots, these are real. There really are areas of the universe that were a little bit colder and a little bit hotter than other places. So these blue areas are cold spots. These red areas down here are hot spots. And if you look at a modern map, this is again from the 1980s and 1990s, this is from the 2010s, you can see that there are these just beautiful red dots here. There's this hot spot over here, which corresponds to this region over here. And then there's a cool spot over here, which corresponds to this cool spot over here. You can see how much our technology has improved over the years to get such a nice, beautiful image of this radiation from this modern satellite, which was called Planck and which was launched by the European Space Agency. So we can see with exquisite detail where the universe was hot and where the universe was cold. And from that, we can learn how the universe may have evolved forward. So after about 370,000 years, we no longer have light interacting with the protons, the neutrons, and electrons, because they're all part of atoms now, and the light just mostly streams through them. We call this the cosmic dark ages because the light from them, from the heat of the universe, is not really talking to those atoms anymore. And those atoms are not yet forming into stars and generating their own light. So there's really not much light in the universe at all. So that's why we call it the cosmic dark ages. But important stuff is happening here. And in particular, the important thing that happens is that gravity is starting to exert itself as the dominant force in our universe. So here's what I mean by that. Let's look at the cosmic microwave background. If we choose a particular spot in here, say this particular hot spot here, what we can infer is that this was an area where there was a little bit more matter, where things were a little bit hotter and where things were a little bit closer together. Because as you remember, when things are close together, they're hotter, and therefore the denser regions are hotter. Let's imagine that we zoom in on this region here and we simulate what's going to happen with our computers, knowing that there's a very slightly more dense region of gas here than there is in the surroundings. When we make a simulation like this, here I'm showing the density of gas in this region here as different colors. So the brighter colors are more dense, the darker colors are less dense. What happens when gravity starts to take over? You have these dense regions and everything starts to come towards them because gravity brings stuff together. So wherever there's more mass, everything starts to come that direction. And what you get is you get this rapid collapse of stuff from this relatively uniform gas that forms straight from the Big Bang into structures that kind of look like the galaxies that we see. This is a relatively old simulation. I'm going to show you now kind of the state-of-the-art simulations that are being performed. This is called the illustrious TNG simulation, where TNG stands for the next generation. And this is what I think many people would consider to be the state-of-the-art in trying to understand how our universe came to be. So what you can see here is you have these beautiful, essentially spiderweb-like lines of gas that are collapsing down on themselves. You get these little tubes of gas, these little tendrils that reach throughout the universe. We call this the cosmic web. And within the cosmic web, you can start to see little points of light. This isn't showing light, this is showing the density of stuff, so how much stuff there is per area. But each of those little points of light is a galaxy, and we can see the galaxies forming like this after starting out from this relatively uniform fluid as a result of the Big Bang. Here's a zoom in of one of the illustrious TNG galaxy clusters. So we can watch this go from essentially a relatively uniform area of gas and form a galaxy like the ones that we see with the Hubble Space Telescope. So here we go. This is a complex visualization. This main panel is showing the density of gas, so how much gas there is in a small area. This panel is showing a zoom out. This panel is showing the starlight, so we're forming stars, and we'll talk about that a little bit later and in the next lecture a lot more. So this is what it would look like if we looked at it with our telescope. So what you can see is that the gas is all kind of streaming into this one area here where there ended up being a little bit more gas in the beginning, and it all just kind of reinforced and fell in upon itself. You can see these little knots orbiting around each other, trying to come to the area with the highest gravity. Now we've paused the simulation and we're going to rotate around and look in different views. So again, this view here is the density of the gas. Now we're going to switch. I believe this is how many heavy metals are in the gas. So things other than hydrogen and helium. We'll explain in the next episode, in the next lecture, how we get that. Let's see, this looks like, this is the brightness of hydrogen gas, how much light is being emitted by hydrogen. And now we can go back to the density of gas. But keep an eye on this panel now, this panel here with the starlight image, because now this is starting to look like one of the galaxies that we're used to seeing from Hubble. And you can start to see these beautiful spiral arms that are emerging as other smaller galaxies whiz by and add gravitational perturbations and tug on the stars within that galaxy and cause these spiral waves to appear. So we feel pretty confident in our ability to simulate how the universe evolves from this Big Bang theory and how we can get the galaxies that we see. So the last thing I want to talk about in this lecture is how we start forming the first stars. And basically, the idea here is exactly the same as the idea was for forming galaxies. We can start off with a relatively uniform amount of gas. It's fairly well spread out in the region, but some areas are going to be just a little bit denser than others, and those areas are just going to collapse, and that collapse is going to cause more mass to be there, which is going to mean there's a stronger gravitational pull towards that area, which is going to bring more and more gas right there to that one region. And eventually, you're going to get gas that's dense enough for a star to turn on. In the next lecture, we'll talk about what it means for a star to turn on. But for now, I just want you to watch the process of this cloud collapsing, and then we can see where the stars end up. Now we're going to zoom in here, and you can look at these little knots that are forming here. And it looks like the first star has just turned on and shot out here. And now you can see more and more stars turning on and shooting out as they interact with each other and spiral around each other with their gravity and eventually eject one another from their birthplaces. And these stars are now what light the universe.